So far, our definitions have been very general. We talked about what mechanical waves are and transverse and longitudinal and combination waves. Now we're going to narrow in a little bit. We're going to look at periodic waves. That means that the motion happens over and over. And the specific kind of periodic wave we're going to look at is a wave, a sinusoidal wave, which means it's been created by something moving with simple harmonic motion. Here's where, if you're a bit rusty on simple harmonic motion, you might wish to go through the review material and try out that first handwritten assignment. So I've got a video here. We'll start by looking at a PhET simulation to look at such a sinusoidal wave. So here are the steps to get to that simulation if you want to try it yourself. So I'm going to pick no end, the wave keeps going, no damping, put it in slow motion because it goes fast, and I go oscillate. So there's my oscillator that goes up and down. What my oscillator is doing is it's moving with simple harmonic motion. That means it has frequency F, angular frequency omega, and period T. So that moves this part of the string up and down with simple harmonic motion. Then what happens, the result of that motion, is we get a wave on the string that has crests and trough. A crest is the high point and a trough is the low point. So this is a crest of the wave and this is a trough of the wave. This wave repeats itself with that same time period as the oscillator producing the string. So this wave repeats over and over with time t. This is a periodic wave with a simple harmonic motion source. That makes this a sinusoidal wave. And I said earlier that we studied waves because light and sound are waves and it's important to understand the motion. It turns out light and sound are both sinusoidal waves. And later on when we talk about superposition, we're going to see that any actual wave we study could be considered as a sum of sinusoidal waves. So that's a good incentive to study sinusoidal waves. When we look at our wave on the string, we see that the disturbance, so the disturbance is the distance from equilibrium, how high up it is. So we'll call the height y. And by height, we mean relative to equilibrium. That height depends on a couple of things. It depends on where we are along the x-axis, and it depends on what time it is. So our y, our height, is y as a function of position and time. We're going to look at each of those dependencies and see what we get for a mathematical description of this wave on the string. We said the height of our graph y depends on position and time. We'd like to find that expression. So let's ask what happens as a function of position and what happens as a function of time. And let's then combine those two expressions to find the overall expression. So first off, let's ask what happens to any one piece of the string as a function of time. So let's say we're going to look at this green dot right here. Let's just pick one bit of the string and ask what happens. I'll hit play on my simulation. You see it moves up and down. The source is moving with simple harmonic motion. So that green dot is also moving with simple harmonic motion. So now we see what's happening. One element, so one specific x, moves with simple harmonic motion over time. That should be familiar from chapter 14. The extra review is posted if you need it. The high point is called a crest, the low point is called a trough, and if we were to make a plot of that equation as a function of time, you would see that the graph looks like we have plotted right here. It goes up and down over time. And this is just for one specific value of x. That's what this little bit of the string is doing. In our graph, we know it takes a total amount of time equal to the period to go from a crest back to a crest. Now, we completely know how to describe this wave, we know the equation for this. We know that y, for that one specific value of x, is equal to the amplitude, that's the highest amount from equilibrium, times cosine of 2 pi over t, that's because it repeats over time, times whatever specific time it is, plus some phase constant. Okay, if you're at all dicey on what these things are, you can go back and review the first half of our first lecture, or you can go through that review material. So in this expression, 2 pi over t, that's the angular frequency omega. And that's the same as 2 pi times the regular frequency. And that has units of radians per second, which is a reminder that your calculator needs to be in radians mode for this section. And that angle phi is the phase constant. That's what allows your oscillator to start at some place other than 0. Okay, so there's our expression, what happens to one piece of the string as a function of time. Our next question is what happens to the whole string at one time. So right now we've looked at what happens at one point in space. Now we ask what happens at one instant in time. This is sometimes called a snapshot graph. So this is if we're playing the simulation and we hit pause. So y for one point in time also has simple harmonic motion as a function of horizontal position x. Okay, so that means our graph repeats over time. So our height y at our one specific time is equal to the amplitude, because even if it's just one specific time, we still have the same amplitude, times the cosine. Now, when our graph repeated in time, it had a characteristic time of the period, and it was 2 pi over the period times time. Here our graph repeats in space. So it's 2 pi over the characteristic length. That's called the wavelength. It repeats over position. So instead of having time here, we have x. And then we still have to add on that phase constant in case it doesn't start at the amplitude. Okay, so lambda is our characteristic length. That's called the wavelength. Our period t was the time for one oscillation. Our wavelength lambda is the distance for one oscillation, or the distance for one cycle. We defined omega as 2 pi over the period. We define k as something called the wave number. And that's 2 pi over lambda. And that's measured in radians per meter. So omega gives you how many cycles per second. K gives you how many cycles per meter. So your wavelength is from one point in the cycle back to the same point in the cycle. So trough to trough or crest to crest, for example. Okay, so now we've got our two expressions. One tells us what happens in time and one tells us what happens in space. Before we combine our two expressions to find the expression for the height of the wave as a function of position and time, let's just cover one more concept, and that's wave speed. How fast is this disturbance traveling along that string? So that value is equal to v, that's the wave speed. We can calculate the wave speed by measuring how far it goes and how long it takes to go that distance. We can do distance over time. If we think about one cycle only, the distance it travels is a wavelength lambda, and the time it takes is a period t. And then we might remember that frequency is 1 over period, so that's the same as lambda times f. That gives us an expression, v wave speed is equal to f times lambda. Anybody who did Physics 1020 or 1050 with me probably has heard me say that the one equation you should remember about physics in 20 years is F equals ma. Now I'll add on, the other equation you should remember from physics in 20 years is V equals F lambda, the wave equation. This one's really important because it describes how a wave moves. Okay, so let's just quickly do an example here. The speed of sound in air, this is V, is 344 meters per second. What is the wavelength of a sound wave with frequency 784 hertz? For those of you who are musical, that's oh, I don't even know what that's called. I'm not musical. G5? Anyway, anybody who knows music, please tell me what that's actually called. And how many milliseconds does each vibration take? So it's asking for wavelength and period. So to solve part A, we'll start with V equals F lambda. We're trying to find lambda, so lambda is V over F. Our V is 344 meters per second. Our F is 784 hertz, which is the same thing as seconds to the minus 1. When we do that in the calculator, we get 0.439 meters. Okay, the second part of the question, how many milliseconds does each vibration take? That's period T, that's 1 over F. 1 over 784 hertz gives us 1.28 times 10 to the minus 3 seconds. That's not exactly what the problem asked. It asked for how many milliseconds. A millisecond is 10 to the minus 3 seconds, so that's 1.28 milliseconds. Part B, what is the wavelength of sound 1 octave higher, where 1 octave higher means twice the frequency? So for this one, lambda is V over F. We're doubling our frequency compared to the first part, so we anticipate that the wavelength is going to be half. 344 meters per second divided by 2 times 784 hertz gives us 0.219 meters, so halved as we expected. So let's just summarize all those equations before we go on to put them together. What happens at one point in space is that y is equal to a times cosine of 2 pi over t, that's omega, times the period t plus some phase constant phi. What happens at one point in time is that y is equal to a times cosine 2 pi over lambda times x. 2 pi over lambda is our wave number k. And we said that v equals f lambda if we remember that f is omega over 2 pi. And lambda would be 2 pi over k. We also get that our wave speed is equal to not just f times lambda, but also omega over k. All right, we're going to take these three equations, going to put them all together in the next slide, and we'll have our description of how our wave moves. Let's go through the process now of finding the general description for the height of the wave as a function of position and time. Let's say we have a wave and it's moving to the right with speed v, and we've taken a snapshot of this wave at time t equals 0. We know the equation for this wave. So the height of this wave at any position x at time t equals 0 is equal to the amplitude a times the cosine of 2 pi over lambda. That's the wave number, and this tells us that the wave repeats over every distance lambda, times x plus some phase constant phi. The phase constant allows for the graph to start at some height other than amplitude. So now what we want to do is ask what happens a little bit of time later. Okay, so on the bottom, I still have that t equals 0 wave. It's moving to the right, so at some little bit of time later, bigger than 0, it's moved to the right a little bit. I'm going to trace that wave in red. So this is the wave that I want the equation for. What is the height of this wave at position x at some time t? So that's what we're after here. So let's first ask, are these two waves the same or are they different? I'd have to say that they're basically the same wave. One is just shifted a little bit compared to the other. So let's pick one point on the red wave. Let's call that at distance x. Let's look at that point on the wave. Does that compare at all to the blue wave? Well, yep, it sure does. Some little bit of distance behind delta x, that wave has exactly the same shape. So our red wave is the same as the blue wave that's a little bit behind it. How far behind? Well, the wave travels with speed v. The time is equal to t, so that little bit of distance behind there, delta x, that must be v times t. Okay, so the red wave is the same as the blue wave at a distance v times t behind it. There's our relationship between the two waves. So y of x and t is the same as y of x minus vt at 0. Okay, so this is the red wave, this is the blue wave. Those two are exactly the same. So let's fill in x minus bt in our equation for the blue wave. See what we get. So that's the amplitude times cosine 2 pi over lambda. Instead of x, we have x minus vt, and we still have plus our phase constant. Okay, here's our expression. This one is not very pleasant, so let's simplify it. And maybe why don't we even add in a little bit of note here about what we did. So we see that y of x minus, or y of x and t, so I just want to make sure we get these notes correct here. Y of x and t is the same as at t equals 0, which is delta x equals vt behind. That's why we have the minus sign, because the blue wave is behind the red wave. Okay, there's our notes put in. Now let's do our algebra. Okay, so we've got a times cosine 2 pi over lambda times x minus 2 pi over lambda times vt plus phi. So we just did our distributive property there. We'd like to make this look a little bit nicer. 2 pi over lambda, that's our wave number k. V over lambda, if we remember that V equals F lambda, then V over lambda equals F. And 2 pi times F, that equals omega. Okay, so let's put those two little bits in. So y equals a times cosine k times x minus omega times t plus phi. That's our equation for a wave which is traveling to the right with speed v. If our equation was traveling to the left, you could do this exact same procedure. What you would find is that your expression would be y equals a times cosine kx plus omega t plus phi. That might be a useful exercise for you to go through just to make sure you understand the process. Okay, just before we do a numerical example, let's do a more conceptual one. A wave on a string is traveling to the right. At the instant shown in the picture, the motion of the piece of string marked with a dot, so this little piece right here, is it moving up, down, right, left, or is it at rest? So I will invite you just to hit pause on the video and decide for yourself what you think is happening. It's really important for you to choose. You have to commit to an answer. I suggest you write it down. If you get it wrong, that's okay. Nobody's going to see what you wrote down. But the process of committing to an answer is very important. You can't hedge your bets. Okay, if you're not sure what's going to happen and you'd like to see what's going to happen, I'm assuming you've already decided, and let's go through the solution. You could open up that PhET simulation. I've got it set up more or less similar. So here's the one dot we're going to look at. Let's see what it does. So I'll just hit play on it. It goes up. Okay, so another way we could look at it, if this were a test and you didn't have that simulation available to you, you could just draw the wave a little bit of time later and ask what happened to that piece of string. Well, it went from there up to there. So the answer is it moves up. That may have surprised some of you, but physics actually still surprises me all the time.